welcome back to the Pilot Forge. We're doing some more navigation with chapter 3, Earth Magnetism. Now, we begin with true direction because we need to make sure that we remember a little bit from the last two chapters. If you don't remember too much about it, pause the video, take a look at the previous chapters. They're already there on YouTube. Now, what I've got drawn up is the Earth with the geographic North and South Pole here, or the true North and South Pole, with the direction of spin in this direction, anti-clockwise. West and East shown to you with the meridians drawn up and the equator as the dotted horizontal line. Now, I also have a cross-section of a map which I have expanded over here. Alright. Now, the reason why I'm talking about true direction is because we don't use true direction up in the air when we fly. We use something called a magnetic compass. Let me show you what it looks like. This is what a magnetic compass looks like. You've got north, south, east, west and a needle that points towards the direction, okay, with reference to north. Now the point is that this instrument orients itself with reference to the magnetic north and south, not the true north and south. So we need to know the difference between magnetic and true, okay? The one thing about the magnetic north and south is that it moves. The magnetic pole moves, alright? Because it moves, we could not place the magnetic north and south pole at a permanent location, which would basically incur a major cost for us, especially when it moved, because that would include changing directions, changing maps, and that is a multi-billion-dollar expense for every single country in consideration. So what we do instead is we find out the true direction of our travel direction and then we just apply the variation. What variation? The variation that I'm talking about is the difference between the magnetic North Pole and the position of the true North Pole. Okay, let me show you. Let's start from true and then get to magnetic. Okay. So just quickly going over how to measure true directions. You've got the cross section of the map over here, which I have expanded. There's the true north, true south, the meridians and the equator. Now we're going from A to B. Therefore, we've drawn a line up that way. You can see it's drawn up over here also. It's curved in this case because it follows the curvature of the Earth. The way we measure true direction is from the north, clockwise, in the direction that we travel. In this case, it's 225. And you can use any direction you want. If you want, you can draw it up this way also, or this way, or this way. It all depends on where you want to travel, but the basis of measurement remains the same. From the north, clockwise, till we get to the direction we want to travel in. In this case, 225 degrees true, with the direction measured with respect to the true north. Okay, so now we need to take a look at how we get magnetic direction. To begin with, the Earth behaves like a giant bar magnet. If you have seen the experiment with the iron filings, what you will notice is this kind of a pattern that is created. These lines, they are called lines of flux. Okay, they always orient your magnetic compass with respect to magnetic north and south. Now, magnetic north is here, magnetic south is here, true north is here, true south is here. And when you have a magnet, you can suspend it up in the air and you can see that it will align itself with the magnetic lines of force, like this. Okay, is that clear? If it is not, make sure you tell us. So, if you were traveling from A to B and you had this magnet placed here, or in this case here, like this, you'd get magnetic direction in the same concept as the true direction, except measured from magnetic north, clockwise, in that direction. Simple. Gets us to the magnetic direction definition. It is measured from the magnetic north, clockwise in the direction of travel. Very similar to true direction, but measured with reference to magnetic north. So the next thing we need to take a look at is variation. Variation tells us the difference in position between the true north and the magnetic north. So you've got the true north and true south over here, magnetic north and south over here, and look, obviously there is a difference. Okay. By definition, difference between true north and magnetic north, variation can be east, west, 0 or 180 degrees. I'll explain it in a second. So we spoke about variation and how it can be east, west, 0 degrees or 180 degrees. Now this is based on your position of observation. Alright. What I've got drawn up here is the Earth. There's the true North Pole from the top and the magnetic North Pole next to it, viewed from the top. We've got 4 positions, 1, 2, 3 and 4. Based on these positions, we can find out the variation of magnetic north to true north. Alright. So, the easiest one is position number 3. From position 3, when you take a look at the positions of true north and magnetic north, they lie in a straight line. Therefore, the variation is 0. You see? Viewing it this way. Now at position 1, you can see that magnetic north is to the right of true north, which means it is to the east of true north. Therefore, variation now is east. Similarly, if you take a look at it from position number 2, you can see that magnetic north is to the left of true north. Therefore, variation is west. Now, position 4 is the most interesting one. This is what shows you 180-degree variation. Now, if you're in between true north and magnetic north, true north on one side, magnetic north exactly opposite to the other, you can see that the variation is 180 degrees. Now we're going to take a look at magnetic dip. Remember that we spoke about how the Earth behaves like a big bar magnet and that it's got lines of flux emanating out of it. What I want to point your attention to is the lines of flux at the equator and the lines of flux at the pole. Okay? Because the bar magnet is placed inside the surface of the Earth, the lines of flux go in at an angle near the poles as compared to over the equator. Alright, so when you suspend a bar magnet and it aligns with the lines of flux, near the equator it is in line with the surface, meaning that it is horizontal along with the surface. But at the poles, because it is aligned with the lines of flux, it makes an angle with the surface. Alright. At the equator, in line with the horizontal surface, at the poles, making an angle. Alright. This angle is called the magnetic dip. Now it is not a good thing to have magnetic dip because it stops the magnetic compass from functioning freely. Alright. So we need to remove this magnetic dip so that the compass can function freely, especially at the poles. So to get rid of this magnetic dip, what we do, we suspend the needle of the magnetic compass in a fluid. Having it suspended in a fluid, what ends up happening is that it tends to balance itself out. But we still do get a residual amount of dip. So you can see over here, there is still a little bit of an angle. That angle is called residual dip. Residual dip is the dip which remains after correcting for magnetic dip at the poles. Alright, so the next thing we're going to take a look at is deviation. Now here, I have drawn up a standard cockpit. Alright, you've got the 6 instruments here, control column here, you've got the radio stack and transponder and some auxiliary instruments. You've got some lights and you've also got the compass drawn up here. The compass is usually placed away from the electrical instruments so that the electromagnetic fields that are created by electrical instruments don't affect the compass as much. Okay? But there are wirings, there are antennae, there's also your headset and your mobile phones and devices. These do create electromagnetic interferences which do interfere with the compass reading. So this deviation from the compass reading is what creates an error. And that is what deviation is about. Now, in a normal aircraft, standard equipment is always taken care of by the addition of 2 soft magnets that are present in the compass housing itself. But it does not account for the headset, mobile phones, and any device, anything that can create an electromagnetic field. Right? So it occurs due to the stray electromagnetic fields in the cockpit, and the difference between magnetic north and compass north is deviation. Once you correct for deviation, you will get compass north. Now, that gets us to TVMDC. These are the directions, true, magnetic and compass. These are the errors, variation and deviation. Together they make TVMDC. So, we start with true, apply the variation to get magnetic direction. And in the cockpit, if we have deviation, we apply the deviation to get compass direction. These are the directions, these are the corrections, or errors or corrections. And you have to apply these corrections to these directions to get the correct answers. Alright. Now, say for example, you have a true direction of 0, 2, 0 degrees true, a variation of 0, 1, 0 degrees east. What would be your magnetic direction? So in this case, a very helpful formula or a methodology will come in handy for you. If you are progressing from true to compass, remember, variation needs to be applied. When you're applying variation, easterly directions least. So you remove or you subtract easterly directions, and for westerly directions, you add. In this case, 010 degrees east is subtracted from 020 degrees to get a magnetic direction of 010 degrees magnetic. It's as simple as that. If you have a deviation 001 degrees west, the same thing applies. Moving in this direction, so true to magnetic to compass, if you have a deviation of 001 degrees, if it is west, you add it. This gives you 011 degrees compass. Now, we finish off the chapter with the definitions: heading, variation, deviation, isogonals, agonic line, angle of dip, isoclinals and aclinic line. All these are in the description below. So to summarize the whole chapter, we now know how to convert true directions which we get from the maps and charts into magnetic directions which we can use in the aircraft. Alright, we also know how to correct for deviation and get compass readings which we can then use more effectively while flying, which will reduce our errors if there are any kind of electromagnetic interferences. Why this is important? The magnetic compass is the only device which we use to travel from one place to another. Alright? In simple aircraft. In complex aircraft, there are many other different ways. We will take a look at them with further chapters.